All right. I hope you have gone through the problem statement. Um, let's read this together again. Now consider a piston cylinder assembly. Let's say we have piston cylinder assembly which contains 2.5 liter of an ideal gas. This is very important to note. This 2.5 liter is of an ideal gas at 30 degrees Celsius and 8 bar, which is pressure. The gas reversibly expands to 5 bar. Initially, the temperature was how much? 30 degrees Celsius. How much was pressure? 8 bar, right? Now, after expansion, when it expands, volume is higher, pressure will be lower. Inside, I'm talking about inside, not outside. If volume will expand, pressure will decrease. How much is that pressure? That is 5 bar. Okay? Now, part 1. You need to write an energy balance. Energy balance mean first law of thermodynamics, right? For this process, you may neglect changes in potential and kinetic energy, which I think which was a part of the theory as well, right? So we can ignore kinetic and potential energy, but we need to write energy balance for this system, which is simple. We have already done that. That is Q plus W is equal to delta U. So normally if you don't ignore kinetic and potential energy, you need to write those terms as well. But as these are neglected, as we said, so there is no need to write these. So this part is our first law of thermodynamics or energy balance, right? So that means part 1 is done. Now let's read the part 2, which is part B. Suppose that process is done isothermally. What does it mean? Isothermal, iso mean same, thermal mean temperature. Isothermal mean in a process in which temperature remains constant or same. Okay? What is the change in internal energy or delta U for the process? 1. What is the work done? 2. During this process. And what is the heat transfer? 3. Mean if the same process, this process which we talked about, it happens at constant temperature or isothermally, you need to tell what is internal energy or change in internal energy, what is work done, and what is heat transfer. Now this is the question, part B. In fact, part B has further parts as well. So let's see in detail. Now what you need to calculate, delta U, Q, and work. And remember, this is isothermal process, mean temperature remains constant. Now, what would be change in internal energy? That is easy answer, right? Change in internal energy would be 0. Why? Because internal energy depends on temperature. Mean if temperature is rising, internal energy is rising, or internal energy is a strong function of temperature, right? If temperature is changing, internal energy is changing. And if temperature is not changing, as is the case of isothermal process, temperature is not changing, that means internal energy is not changing. So if internal energy is not changing, that means U1 is equal to U2, and that means delta U is equal to 0, right? So this is an explanation. One of the part B is done. Now the second part of part B was work done. Now can we use this work done formula? The answer is no, because if you remember in the statement, we have ideal gas, and for ideal gas we have a different formula which is written here, right? So for an ideal gas, work done is equal to nRT ln P2 over P1. So this is an ideal gas work done formula for an ideal gas. Now, if we see this, do we have number of moles? Maybe not. Do we have universal gas constant? Answer is yes. Do we have temperature? Answer is no, but we have indirect information that it's an isothermal process. But what is the temperature? We don't know. Do we have P2 value? This is 5 bar. Do we have P1 value? This is 8 bar. So that means we don't have N, we don't have temperature, mean we cannot easily solve this question. But there is a small trick. Can we say, because it's an ideal gas, can we say PV is equal to nRT, which is an ideal gas? So that means this nRT, which is equal to PV, this nRT can replace PV, right? And what PV? Maybe initial pressure and initial volume and initial temperature, maybe, I think. So that means we can replace this, we can using this mathematics trick. We can just replace nRT by PV. So that's why you might have observed this thing is here, right? The same formula, but P1V1 that has replaced nRT ln P2 over P1, exactly the same. Now, do we have P1? Answer is yes, 5 bar. But in this case, we have used Pascal because volume is in cubic meters. Pascal is Newton per meter square. So volume should be cubic meters somehow because we want to play around with these meters. Okay? All right. So, and 1 bar is equal to 10 to raise power 5 Pascal. So 8 bar will become 8 into 10 to raise power 5 Pascal, right? So that is P1. This is V1. Do you remember how much was the volume? Do you remember that? Let me go back. How much was the volume? 2.5 liter, right? So volume was 2.5 liter and 1 cubic meter is equal to 1000 liter. So if we convert this, so we will get 2.5 into 10 to raise power minus 3 cubic meters. This thing will become this, okay? That's how it's converted. So this is V1 and then ln P2, which is 5 bar, and P1 is 8 bar. Now you might have observed in this case we haven't changed units of pressure, so it doesn't matter because the reason is whatever the units are, they will cancel out each other, right? So there is no need for that. Pascal, it's Newton meter. Pascal is Newton meter, and this is cubic meters. So if we multiply this with cubic meters, so this becomes Newton meter, and Newton meter is equal to joule. And that's why it's Newton over meter square, and that's the cubic meters. So that's why we get a joule here, right? So this is how you calculate work done in case when you have an ideal gas, right? Now you know work done, which is this, you know delta U. And ideal gas law got total 3 terms. So you know this, you know this. Can you calculate this? Which is just biomathematics, right? So that's why Q plus W is equal to delta U. This is already 0. You already have calculated this, which is 940 kilojoule. In fact, minus 940 kilojoule. So we will get 940 is equal to 0. So the Q will be equal to 940 joule. So that means that's your answer. So in this case, you have calculated all 3 terms, delta U, W, and Q. Delta U is 0 because internal energy is a strong function of temperature. And if temperature is constant, which is the case with isothermal process, if temperature is not changing, internal energy is not changing. And if internal energy is not changing, that means delta U is 0. Second case was work done. We have calculated minus 940 joule, right? Using this formula, right? This formula, and which was converted into this using PV is equal to nRT. Then by just putting the numbers, we got this minus 940 joule. And then out of 3 terms, we already got 2 terms. The other one can be just calculated from arithmetic means or mathematics. So that's how you calculated all 3 terms of first law of thermodynamics. Now let's read back. This part is done. This part is done. Now let's talk about this C. If the process is done adiabatically, adiabatic mean if we have a process, no heat can come in, no heat can go out. It's isolated, right? Adiabatic, right? Now, if the same process is done adiabatically instead of isothermally, which was in this case, will the final temperature be greater than, equal to, or less than 30 degrees Celsius? Explain. There are 2 questions, right? Now we need to calculate temperature. If the same process, which we said isothermal, if instead of isothermal process, the same process happens adiabatically, will the final temperature be greater than, equal to, or less than 30? Because that's the temperature which is the starting point here, right? So let's see what it looked like for adiabatic, right? Let's write the first law of thermodynamics again. For adiabatic process, what is 0? For adiabatic process, Q is 0. As I said, for adiabatic process, no heat can come in and no heat can go out. So the remaining equation becomes W is equal to delta U, right? As it's here. Now, this is the equation which we need to look, right? Now, in this case, because we don't have enough information, so we need just common sense. The system must do work on the surrounding to expand, like what is happening in process. It is expanding, right? So this is your surrounding, and this is your piston, and this piston is expanding, right? This is your system, right? System is doing work on your surrounding. If system is doing work on the surrounding, that means work is negative. So if you see this equation again, if we have negative W, what do you think? That means, because W is equal to delta U, right? This can be negative only because this is U2 minus U1. When W can be negative, when U2 is smaller than U1 or U1 is greater than U2, this term is bigger, this term is smaller. So if U1 is big and U2 is small, and they are linked with temperature as well, because they, as you know, internal energy is a function of temperature, right? So if U1 is big, that is linked with T1, and U2 is small, that is linked with T2. If U1 is big, that means T1 is big as well. If U2 is small, that is T2 is small as well. So if T1 is greater than T2, what does it mean? Temperature is decreasing or increasing? Temperature from initial stage, from T1 to T2, it's decreasing. What is T1? T1 is 30 degrees Celsius. So what should be T2? That should be less than 30 for sure, based on the logic which I explained here, right? So this is the explanation of how you, based on your common sense, that how you can tell that final temperature in this case or adiabatic process would be less. T1 is 30 degrees Celsius and T2 would be definitely less than 30 degrees Celsius because work is done by the system on the surrounding. So that means work is negative. And the work can only be negative when U2 minus U1 is negative as well, right? And this can only be negative when U1, U2 is smaller than U1. This is the logic. And that's how it's explained in this question. I hope I have clarified some of the questions.